topic for today's lecture is hysteretic damping. It is also called as hysteresis damping. It is also called as structural damping. Hysteresis. You must have heard about the hysteresis loop, and this is basically a loop which is presented as a graph between either stress or strain or force or displacement. Now, this is as far as mechanical engineering goes, a hysteresis loop represents the energy loss in loading and unloading cycles. So, if a material is stressed, which represents the loading cycle, and then it is unstressed, then the cycle goes to the unloading part. And if it is loaded in the opposite direction, so this part represents, once again, this is loading but in the opposite direction, as happens in the case of oscillations and vibrations. So the opposite direction loading, and then from opposite direction unloading again. Now you see, initially, if your object is at rest, so the path traced initially might be this. But after the initial path leading up to the maximum point, then this curve will be repeated. Now, essentially, what a hysteresis loop represents in the case of energy loss is the energy lost per unit volume per cycle for any type of loading and unloading cycles. So, hysteresis loop is not something specific to vibration engineering or oscillations. Hysteresis loop can occur for any type of cyclic or non-cyclic processes, but which involve loading and unloading of some elastic type of material. So, what is hysteresis doing in our vibration engineering curriculum, and what is the concept of hysteretic damping? Hysteretic damping, hysteresis damping, or structural damping, as I've mentioned. So, these names you should remember, because in your examination, the question pertaining to this particular topic could come with the usage of any of these three terms: hysteresis damping, hysteretic damping, or structural damping. Now let us understand what is the source of this type of damping. See, in the case of viscous damping, with which we actually started our topic of damped vibrations, you need to have an external resistance in the form of fluid friction, or the resistance of the viscosity of the fluid. So, if you are trying to move one solid object relative to another solid object, and there is some fluid having some viscosity between the two surfaces, then the external resistance offered by the viscosity of the fluid comes out as viscous resistance or viscous damping. So we can conclude that viscous damping is a kind of external resistance which comes into the system which you are trying to vibrate or oscillate. Now, what happens in the case of frictional damping or Coulomb damping? Once again, we have to talk about relative motion between some two surfaces. So let us say that a mass is sitting on a rough surface or a smooth surface for that matters, and you are trying to oscillate the mass to and fro while the mass is rubbing on the surface on which it is sitting. So there will be Coulomb damping. And once again, as you can see, the resistance to motion comes from an external agency. That means at the interface of surfaces when the contact is made. So there is a coefficient of friction. Most probably there would be a coefficient of friction, and based on that, the force of friction comes out as mu into R, where R is the normal reaction. Okay. So once again in this scenario two, we see that the external force of friction is affecting the amplitude and the energy of the entire system. So this is also the Coulomb damping case is also a case of resistance coming from outside the system or outside the body of the material at least. Now this is where significantly structural damping or hysteresis damping varies. Now see, in structural or hysteresis damping, what happens is we have interatomic or intermolecular friction. What does this mean? Now consider that I have some shaft made of some elastic material. Elastic material could be any metal, steel, iron, anything. Now you're trying to twist and untwist. You're trying to twist and untwist this material while the bottom part is fixed to the ground. Okay. And obviously, at an intermolecular or interatomic level, you can imagine that the atoms or the kernels inside the body or the volume of this material are fixed in space. So the atoms do not want to change their position because they are at a low energy state. But you are applying an external force or a torque, and you are twisting and untwisting the material against the wish or the against the will of the atoms. Now what will happen is the atoms which are occupying specific locations inside the body, they will be forced to move from their position of lowest energy, and they will be forced to rub against each other. So that means you are increasing the energy level of the atoms. Now, as soon as you release your external torque, these atoms will come back to their original state. Now, this action, this repeated action in which you are forcing the atoms or kernels of the material to leave their lowest state and go to some other position and then come back and then go into the opposite direction. This would eventually result in some sort of internal friction between the molecules or atoms. And this friction, which is occurring actually at the interatomic or intermolecular level, eventually would result over a long period of time in the release of lost energy in the form of heat. So this phenomenon can be observed very easily if you take a thin aluminum or copper wire. You can actually test this theory whether hysteretic damping occurs or not. You take a very thin copper or aluminum wire and then you try to bend it in one direction and then bend it in the other direction and keep repeating your action again and again. And after, let us say, three or four, or let us say five cycles in which you have bent and unbent forcefully this thin wire, you will see that the temperature at this region would have risen up significantly. Now, where is this heat coming from? This heat is coming from the internal friction of the atoms and molecules. So this is the concept of hysteretic damping. So the energy of oscillations in the case of hysteretic damping is released as heat or lost to the environment in the form of heat because of intermolecular or interatomic friction. So this is the basic phenomenon of what we call as the hysteretic or structural damping. And now this is where the hysteresis loop comes in. So we saw that in any type of oscillations involving the deformation of bodies, this was the case of torsion, and the wire example was a case of bending. For longitudinal vibrations also you can consider the same system. The only thing is the deformation would be in the longitudinal direction. But anyway, no matter how you try to deform some material at rest, hysteresis dampen will come into play. Now, if energy is being lost in every cycle, how do we capture it? So if you draw the hysteresis loop for hysteresis damping, this is approximately the shape of the hysteresis loop. So it's not a specific geometric shape, but some materials would give a hysteresis loop like this, which looks like an ellipse, a deformed ellipse. So approximately you could say that it is an elongated sort of ellipse, an elliptical like structure, but not exactly an ellipse. Okay, and depending on the material and the type of loading and unloading that you are actually putting into place, the shape of the hysteresis curve also changes. In some places or in some textbooks, you would even see hysteresis loops like this, a leaf-like structure being created. So this is the loading and unloading cycles, but occurring like this. In some cases, you will see hysteresis loop like this. In some cases, you will see hysteresis loops like this. But nevertheless, there is an unloading and loading cycle, and it occurs in both the directions, as in the case of vibrations and oscillations. So the significance of hysteresis loop is that the area covered or the area inside the hysteresis loop represents energy lost per cycle per unit volume. Okay, this has to be remembered as it is. This is energy lost per cycle per unit volume, the area of the hysteresis loop. If you want to check out whether this thing actually checks out dimensionally, you could simply multiply stress with strain. Strain is dimensionless, so stress has a unit of Newton per meter square. And now please check it out yourself. What is the unit of energy per unit volume? Okay, per cycle is simply a number. Energy is, let us say, the dimension of energy is Newton meter, and per unit volume, that means the dimension of volume is meter cube. So eventually this is exactly the same as this. So dimensionally it checks out. So that means if you actually find the area covered by the hysteresis loop, you are going to get this quantity, energy loss per cycle per unit volume. And obviously it is per cycle because one complete loop represents one complete oscillation or one complete vibration. Okay, now we are going to undertake a small mathematical treatment here, because hysteresis damping is not so easily captured mathematically like we captured the case of Coulomb damping and viscous damping. See, in the case of viscous damping, what were you doing? In reality, what is happening? There is some fluid, some real fluid in the form of lubricant, which has got some viscosity and all, and there is relative motion between two surfaces. But for the sake of mathematical treatment, you converted this entire real world scenario into a model like this. So you said that whatever elasticity was existing inside the component vibrating, I converted it into a spring of spring constant K. Now, whatever viscous damping was being offered by the real fluid in your system, you converted this viscous resistance in the form of a representative damper of damping constant C. So we see that in the case of viscous damping, you were very easily able to convert the real world system into a mathematical model. Now, once you get a model like this, you can simply go on constructing the differential equation, finding the natural frequency and all. Now, what do we do when this thing occurs at an interatomic level? So the only recourse with standard technology that you have, see, the new technology that is coming up every day will offer you newer and newer opportunities for observation and experimentation. But with the current level of technology that is available openly among experimenting scientists and engineers and technical people, you can say that the vistas of observation are not very large. You have still limited amounts of uh, opportunities available for observation. What I'm trying to say is, if it was a simple case of viscosity offered by fluid, you can easily convert it into a mathematical model of C, or an equivalent damper can be put here. What do you do when this is not the case? It's not something that you can observe with your naked eye. You have interatomic and intermolecular friction to deal with here, which you cannot measure in a standard laboratory. In your vibration lab you cannot simply go and check कि भाई मैं एक बार नाप लेता हूँ आज atoms के बीच में कितना friction हो रहा है. It cannot be done. So what you have to do is, you have to find some mathematical way to come up with some sort of damping constant for hysteresis damping. कि भाई अपन ने विस्कस फ्लूइड की विस्कोसिटी के कारण जो रेजिस्टेंस था उसको तो इस मैथमेटिकल एंटिटी में कन्वर्ट कर लिया. सो दिस इज व्हाट वी वांट टू ट्राई आउट कि भाई हिस्टेरेसिस डैम्पिंग के कारण जो लॉस होता है उसको अपन ऐसे किसी डैम्पर में कन्वर्ट कर सकते हैं क्या. सो वंस द मॉडल इज प्रिपेयर्ड देन यू कैन गो ऑन performing your mathematical analysis without any problem. So let us see what is this mathematical treatment that we are talking about. First of all, let us compare this with energy loss of viscous damping. See, since we are talking about energy loss in hysteresis loop, once you are able to make the hysteresis loop, you can at least get an idea of how much energy is lost per cycle per unit volume, whether you are unable to see the interatomic friction or not. Okay. But in the case of viscous damping, let us see how this energy could be calculated. Because viscous damping is totally understood by us, so it's easy to calculate a mathematical expression for energy loss for viscous damping. So what are we going to do? First, let us forget about hysteretic damping. We are coming back to viscous damping. And in this case, we are going to find out how can I model the energy lost per unit volume, per unit uh, per cycle of the vibrating or oscillating system. So this is our standard model for a system which has viscous damping. So you have a damper here, you have a spring to represent the elastic components of your system, and M represents the weight or the bulk of the moving parts. Now let us say total force acting on mass at Y. Now you see, once again we have to go through all the exercises of drawing the free body diagram, taking a random position and all. But from previous discussions it should be fairly clear enough that the force of opposition or the opposing force that is occurring at any location at a distance of y, and in this particular case you assume that the velocity dy by dt is also acting in the downward direction, so that the viscous force due to the damper is upward, and the spring force due to K is also upward. So if you draw the free body diagram in this case, you should easily be able to connect the dots and say that at a random displacement of y, the upward force or the net force acting on the mass is given by ky into c into dy by dt. Okay. Now we already know that for the sake of mathematical simplicity, we assume the motion to be harmonic. Now, if harmonic motion is considered, then the displacement y can be written as this function, where omega is the angular velocity of oscillations and capital Y is the maximum distance to which the mass is traveling in both directions taken from the mean. So above the mean position, this is the mean position. Above the mean position, it is going to a distance of y, and below the mean position also, it is going to a maximum distance of y only. So if motion is harmonic, your general variable y, which represents the displacement at any given instant of time t, can be represented by capital Y sine omega t. This is the characteristic of a harmonic motion. If your motion is harmonic, you can consider it like that. Okay. Now, if you put this y in this equation, so here you have to differentiate it with respect to time. You can see that this force comes out equal to this expression. Now, here we are converting this cos omega t into a different expression. Let me simply explain. I have done this in one single step. So if there is some confusion how this particular step came to be, I will tell you. See, this term is c omega y cos omega t, right? C omega y cos omega t. But I can replace cos omega t with under root of 1 minus sine square omega t. We know that. So that means this expression can be written as c omega y multiplied by under root of 1 minus sine square omega t. Now I am going to take this y inside the radical part here and here. So if I take y inside, y will become y square and get multiplied here and here. So eventually what I have simply done is I'm writing this expression as c omega. Taking y inside the radical part, this becomes y square minus y square sine square omega t. This is what we have done. See. And now, since we have y square sine square omega t, so this can once again be written as c omega under root of y square minus y sine omega t whole square. And since this expression is nothing but the expression of your variable y, so you can eliminate this whole thing and put your small y here. So this is how this step came to be. So your force acting in the case of a viscous damped system is equal to this expression. Okay. Now there are two terms, the ky term and this term containing the radical part. Okay. So you can say that this is the spring force and this is the damping force. Okay. At any given instant of time when the mass is at location small y, then the spring force component of the total force F is given by ky, and the damping force component of the total force F is given by c omega under root of capital Y square minus small y square. So now we are going to abbreviate these forces. Spring force we are going to write as F suffix S. Damping force we are going to write as F suffix D. So that means at any given instant of time, the total force experienced by the moving mass in the case of viscous damping say I have told you we are not discussing structural damping here. We are taking a break. Let us say we are, for a moment we are taking a break and going to viscous damping, going back to viscous damping. And what are we trying to do? We are trying to find out a similar expression for viscous damping. We know that in the case of hysteresis damping there is energy loss according to the hysteresis loop. So we are trying to see whether a similar hysteresis loop can be identified for viscous damping. That is what we are going to do. And once we are able to do that, we will say that yes, I have a hysteresis loop for viscous damping, I have a hysteresis loop for hysteretic damping, and since these two are comparable now I can enable a sort of mathematics with which I can convert the hysteresis loss into some sort of damping mechanism, so that I can put a damper for hysteresis loss also. जैसा मैंने विस्कस डैम्पिंग के को कन्वर्ट करके एक छोटा सा डैम्पर सिस्टम में लगा दिया था, उसी तरीके से मेरा ओवरऑल ऑब्जेक्टिव इस मैथमेटिकल एनालिसिस के बाद ऐसा ही है कि भाई विस्कस डैम्पिंग के लिए भी अगर एक हिस्टेरेसिस लूप जैसा एक्सप्रेशन आ जाए तो हिस्टेरेसिस लॉस और विस्कस लॉस को इक्विवेलेंटली कन्वर्ट करके अपन एक डैम्पर मैकेनिज्म में कन्वर्ट करें. दिस इज आवर ऑब्जेक्टिव. सो एनीवे लेट अस सी कि आगे अपनी मैथमेटिकल एनालिसिस क्या कहती है. अभी अपन विस्कस डैम्पिंग डिस्कस कर रहे हैं. विस्कस डैम्पिंग इज डिस्कस्ड. ओके, so total force Fs plus Fd is F. Now look at this rearrangement. Damping force is C omega under root of capital Y square minus small y square. We have already obtained it. Now what I'm going to do is I'm going to square both sides. First step is to square it up and then rearrange it like this. Bring C omega whole square below Fd square, and what you are remaining with is capital Y square minus small y square. Now do one more thing. Bring this minus y square to the left hand side. Okay, you will see where we are going. Now this particular page of the PDF file is maybe a little bit blurred, so I will do one thing. This is a good thing that we are recording this video, so I will write it here so that it would not matter whether the page is blurred or not. So eventually what we are having is, let me write it down and then I will show you. This is f d square upon c square omega square y square plus small y square upon capital Y square equal to 1. Okay, initially what we had was this expression and we want to see how we are going to treat it. The expression is f d square upon c omega whole square equal to capital Y square minus small y square. Okay, now let me show how this was obtained. This is the expression that we had right now. Now I bring this minus y square to the left hand side. So what happens is this becomes plus y square equal to capital Y square. And then as the next step, I'm going to bring this capital Y square below here. I'm going to divide this whole expression with capital Y square. So what will happen if I do that? On right hand side, I would be left with 1 because now I'm dividing. Here I'll get capital Y square, here I'll get capital Y square. This is what is going to happen. And this is given as this expression. So this is how you obtain the expression given in the text. And now if you look at this expression is nothing but the equation of an ellipse. Now let me give you the equation of an ellipse in a format with which you are comfortable. If I had, instead of showing you this equation, if I had shown you this equation, x square upon a square plus y square upon b square equal to 1, then you would have definitely jumped up to the conclusion that yes, this is an ellipse. Okay, and this is like this is the x-axis, this is the y-axis, and if this is the ellipse, the semi-major axis of the ellipse on the x side is a, and the semi-major axis on the y side is B. This is the ellipse for which the equation is written like this. Now, if you are given an equation like this, can you construct an ellipse? Feel free to pause the video here and construct an ellipse given for this expression. See, the entities standing in the numerator are variables. The entities given below in the denominator are constants. Okay. So if you are capable of, or if you were successful in constructing the ellipse, then it should look like this. So FD has to be taken on the y-axis and y has to be taken on the x-axis. You could put it the other way around also, y on the y-axis and FD on the x-axis. But since it's a general protocol to put your dependent variable on the vertical axis and the independent variable on the horizontal axis. So that is why we have chosen to put small y on the horizontal scale and FD on the vertical scale. Because FD damping force is dependent on the location y, not the other way around. So now you know the reason why this was selected as the x-axis case and this was selected as the y-axis. Anyway, this is just basic mathematics. But the thing is, after rearranging this, we see the appearance of an ellipse. But this elliptical structure in graphical format only represents the damping force Fd. Now, what about the spring force? Now, if you look at the spring force, you can construct a similar. So in a way, let me clarify it a little bit more by constructing and rearranging all this equation. What you wanted to do was, see, your total force acting on the mass is composed of the spring force and the damping force due to the viscous damping. This damping force is a function of your displacement y, right? You can see it here. Damping force totally depends on small y. This is constant, and this is constant. So this force of damping is a function of small y. Now, whenever you have a case like this, you can draw a graph. And we saw that the graph for FD as a function of y was an ellipse, where FD was taken as the dependent variable and your displacement from mean y was taken as the independent variable. And you found obviously from this expression, the bottom part of FD is c square omega square y square. So that means this must be c omega capital Y. And below your square of independent variable, you have capital Y square. So that means the semi-major axis of Y should be capital Y. This is standard mathematics. So what you got was, if I plot a curve between FD and Y, I would get an ellipse. This is the gist of the matter here. Now I want to see, if I plot the graph for Fs with respect to Y, how would it look? Let us see whether Fs is also a function of Y or not. The spring force is given by K into small y. It's a simpler expression, but obviously K is a constant and therefore Fs is a function of Y. Just as in the case of damping force, the spring force is also a function of Y. So we say spring force is also a function of Y. So I can plot a graph between Fs and Y. Now I see that Fs is simply given by constant K into Y. Now this is the equation of a straight line. And specifically this straight line. I'm talking about this straight line. So if Fs is plotted on the vertical axis and y is once again being the independent variable. If it is plotted on the x axis, then fs is equal to ky can be represented by this straight line passing through the origin. Now, mathematically, if I take the displacement in the negative direction, then the force will also extend in the negative direction like this. So this is the actual graph of Fs is equal to Ky. Now, I am interested in plotting the graph of the overall F as a function of y. Now, obviously, we know that F is nothing but the simple sum of Fd and Fs. And since Fd is also a function of y and Fs is also a function of y, so it is 100% imperative that we can say that F will also be a function of y. So now I am interested in plotting the graph of f versus y. Now this is very easy to do. If you apply a little bit of extended logic, you see that fd is an ellipse like this, fs is a straight line like this. What will happen if I add an ellipse and an inclined straight line? We will not go into very detailed mathematical conversion of this because I can do that here, but it will take a lot of your time out of this lecture. And our objective is not to understand how mathematically these things turn out, but to understand the end result of how hysteretic damping is eventually going to be converted into a sort of damper which we can use in mathematics. So I will simply leave the explanation up to this part. I have to add this ellipse and this straight line. The end result would look something like this. So what is going to happen is, see, if you try to spend a little time on this, yeah, you will eventually come up with an explanation. Or if you are really interested to understand the mechanism, then you can give me a call at any time so that I will explain this concept to you personally. How an ellipse which was sitting horizontally and a tilted line, when they are added, will result in a sort of elliptical structure which is tilted about the axis like this. This is going to be the result of the addition of FT and SS. And to our pleasant surprise, this very much resembles the hysteresis loop in the case of structural damping. This is what we were actually looking for, to find some sort of similarity between viscous damping and hysteretic damping. So we have basically achieved that. See, now the graph for F and small y looks like this. Okay. And once again, the area would represent the same thing, but in the case of viscous damping. Okay. Now this is almost similar to the graph of hysteretic damping. We have seen that. Very good. Now let us see what is the expression for energy lost in viscous damping. Till now we have been able to achieve the graphical loss of energy in the case of viscous damping looks somewhat similar to the graphical loss of energy for structural damping. यहाँ तक तो अपन कंफर्टेबल हो गए. अब अपन ये निकालना चाहते हैं कि भाई अब अगर विस्कस डैम्पिंग हो रही है, इस तरह की डैम्पिंग हो रही है, तो अब ये बताओ कि एनर्जी लॉस्ट पर साइकिल पर यूनिट वॉल्यूम है कितना. So for that what you have to do is you have to take the product of the vertical axis and the horizontal axis components. इन दोनों का प्रोडक्ट लोगे. जैसे मैंने अभी पहले समझाया था, stress multiplied by strain is equal to energy per unit volume per cycle, right? So what I have to do here is I have F on the vertical axis and small y on the horizontal axis. और आप जानते हैं कि अगर फोर्स को डिस्प्लेसमेंट से मल्टीप्लाई करूं तो भी मुझको एनर्जी ही मिलेगी. So this is what I'm going to do. In the case of viscous damping, I'm going to construct energy lost by integrating over the area the product of F and small displacement dy. So this will give me E suffix V. और E suffix V से मैं क्या represent कर रहा हूँ? I am representing the energy lost per cycle per unit volume in the case of viscous damping. So let us do that. F is given by this expression and dy is given by this expression. How? एक बार देख लेते हैं. याद तो रखना मुश्किल है इस टाइम पे. Capital F was FD plus Fs, right? So capital F is, यहाँ पे मैं लिख के दिखाता हूँ. I'll show it here. Capital F is equal to FD plus Fs, right? Fs क्या है? K into Y. Y क्या है? कैपिटल Y sin ओमेगा t. ठीक है. FD क्या है? You take it from here. क्योंकि ये जो फॉर्मेट है ये तो कन्वर्टेड फॉर्मेट है, तो इसमें अपन कंफर्टेबल नहीं रहेंगे. एक्चुअली यू स्टार्टेड विद दिस एक्सप्रेशन ऑफ FD. FD क्या है? C इंटू डी वाई बाई डी टी. और y अगर कैपिटल Y sin ओमेगा t है तो dy by dt करके c से मल्टीप्लाई करोगे, यू गेट c ओमेगा कैपिटल Y cos ओमेगा t. दिस इज द एक्सप्रेशन ऑफ योर FD. तो अपन ये वाला एक्सप्रेशन लेंगे so that we can conveniently deal with the trigonometric expression. ठीक है. So this being c omega y cos omega t. And therefore the total expression of F is c omega y cos omega t plus Fs, which is nothing but ky sin omega t. You bring your y here, this becomes ky become ky. So Fs is ky sin omega. So this is how we arrive at the expression of capital F. कैपिटल F का एक्सप्रेशन अपने पास में किया ky sin omega t plus this, and dy is obviously this because y is capital Y sin omega t. So if you differentiate this expression, you get dy as omega y cos omega t. Okay, so we have to do, and obviously if you differentiate omega capital Y cos omega t dt, t will be differentiated once, so you will get dt also. So all you have to do is integrate this expression. But now you see, earlier in finding the area, the variable of integration was y. So we had dy. But after substituting the value of y here, now the variable of integration is time. So we have to apply the limit for time. So while integrating this entire expression, you can put any value of time. Starting from 0 time, you can go to quarter cycle, half cycle, full cycle. Okay. But we want the energy lost for one complete cycle. Loading cycle, unloading cycle, going to the back side and then coming again. This whole cycle. Now whole cycle means one full time period. One full time period of oscillation means 2 pi upon omega. So 2 pi omega is one full time period. So if you say that you have an expression of energy which you need to integrate for one full time period, then you have to integrate it from 0 to one time period, that is 2 pi upon omega. Now, although I could ask you to perform this integration on your own, I will quickly go through the steps of integration so that you will feel more comfortable with the mathematics. Otherwise, it would be actually a very good exercise to ask you guys to integrate this whole expression on your own and see whether you get this expression or not. But anyway, for your understanding, I advise students who are actually willing to take up a small challenge. See, because engineering students at your level should be able to do the part of integration on your own, because it is understood that integration and differentiation is already perfectly inculcated into your learning culture. But anyway, let us start the differentiation. I will show you the steps of differentiation quickly. You have to integrate the energy lost in the case of viscous damping. This is what we are finding. Okay. And this is given by the expression integral 0 to 2 pi by omega of ky sin omega t plus c omega cos omega t multiplied by omega by cos omega t dt. So you first of all multiply this with the two terms that are inside the first bracket. So we get integral 0 to 2 pi by omega k omega capital Y square sin omega t cos omega t. This is the first term plus c omega square y square cos square omega t. And then you have your dt standing. Okay. Now, since we have two terms here, we will treat these two terms for integration differently. So let me say this is the first integral I1 and this is the the second integral I2. So the overall integral which represents the energy in viscous damping is I equal to I1 plus I2. So let us treat I1 first. I1 is integral 0 to 2 pi by omega k omega y square sin omega t cos omega t dt. Now you see, whenever you get a trigonometric expression with cos theta and sin theta getting multiplied and you have to integrate it, the easier way to go about performing this is to convert it into a structure like this. So I am multiplying and dividing by 2. So we know there is a standard trigonometric entity. What is 2 sin theta cos theta? This is equal to sin 2 theta. So using this trigonometric identity, I am going to convert this. So my first integral I1 equal to 0 to 2 pi by omega 2 k You'll get this. And now let us take all the constants outside. This is what you get. Now the integral of sine 2 omega t dt integrated from 0 to 2 pi by omega. You do this on your own, and eventually you should find that this integration result into will result into 0. So I1 you get as 0. And we had started with this I is equal to I1 plus I2. And since I1 is 0, all you have to do is integrate the second part to get the total integral. Now let us come to the I2 part. I2 is C omega square y square cos square omega t. Okay. Now in order to do that, your I, which is now I2, becomes integral 0 to 2 pi by omega. Now you see once again there is a trick for integration. When you have expression for cos square omega t, you can use this trigonometric identity. You know that cos 2 theta is equal to 2 cos square theta minus 1. So I can write cos square theta wherever it appears for my integration as cos 2 theta plus 1 whole divided by 2. So you make this sort of replacement in your cos square, you will get the integral equal to now this is your integral. So basically what we are saying is that if you solve this integral, you will be able to get the energy lost per unit volume per cycle for viscous damping. So let us continue. We will take all the constants outside. Now once again, this integration is totally up to you. Now I leave the integration of this entity, and eventually you will see if you are able to perform the calculations correctly, then this expression should result in pi omega c y square. So this is what we had directly put over here, that the energy lost in viscous damping is pi omega c y square. Now, what do we do from here? Now we come back to hysteresis damping. Now we are talking about hysteresis damping. Experimental evidence shows. Why are we talking about experimental evidence? Because I already told you in the case of hysteresis damping, we cannot observe or we cannot actually measure what is going on inside when atoms and molecules are rubbing against each other due to the motion of the body. So what you can do is you can only conduct some external experimentation and see how much heat is being generated. So with the help of some sensors and some other measures, The details of the experiments are as unknown to me as to you, and we are not going to delve into the details of that. We will simply take for granted the results that scientists and experimenting people have given us. So they have said that when hysteresis damping energy loss was recorded, most probably hysteresis energy loss is recorded as heat loss. So this energy loss was found to be independent of the frequency. So if you are oscillating it at a fast rate, or whether you are oscillating it at a smaller, lower rate, it would not matter. So for every cycle per unit volume, the total energy lost, whether you are moving it fast or whether you are moving it slow, it does not matter. It is the same. So omega is not affecting EH. Another thing about energy lost in actual hysteresis damping that people found was that it was directly proportional to the square of amplitude energy lost. Okay, and basically it can be guessed very easily also, because actual experimentation showed that the hysteresis energy, not energy loss, the uh, amplitude is affecting the force of resistance in the case of hysteresis. Okay, so more the amplitude was, the force of hysteresis was being more, or the resisting force due to hysteresis was more when you took a larger amplitude of oscillation. And since energy of hysteresis can be guessed by taking the product of F and Y, so it's sort of logical to conclude that the energy loss in hysteresis would be proportional to the square of Y. See, this is how. So if force of hysteresis is proportional to amplitude, the energy lost in hysteresis should be proportional to the square of amplitude. This is the logic behind this. But anyway, this result is not based on the extension of logic that we used. This result was observed from actual experimentation. So we are going to take these for granted and construct our mathematical expressions using these results. Okay. Now we want to draw similarity between energy lost in viscous damping and energy lost in hysteresis damping. Energy lost in viscous damping is already totally understood by us. We know exactly the mathematical expression which is going to represent energy lost in viscous damping. But for hysteresis damping, we only know this much. We don't know anything else. Experiments have shown only one mathematical correlation, that energy of hysteresis is directly proportional to the square of amplitude. That's all. So you can, at most what you can do is you can say something like this, that energy of hysteresis would be equal to some constant multiplied by y square. This is the maximum that you can claim about hysteresis energy loss. But anyway, we want to draw similarity between the energy loss in viscous damping and energy lost in hysteresis damping. So what we do is we express energy loss in hysteresis damping in a similar fashion as EV. So you see in EV there is a pi here. So we say that anyway in energy loss of hysteresis one constant is about to come. So there is no harm in putting a pi here, and then the remaining constant can be obtained as some unknown constant h. So what you are doing is you are expressing this constant in energy of hysteresis as pi into h. Why are you writing it as pi into h? Because you want to draw similarity between the expression of viscous damping and hysteresis damping. And in viscous damping, you already have a pi here. So that is why you are forcefully introducing a pi, and then the remaining constant is expressed as h. So now we have energy loss in hysteresis equal to pi h y square. So you see this pi into h is the constant. Okay, and energy of hysteresis is proportional to y square. This is all we knew here. And if you compare energy of viscosity and energy of hysteresis, then you can easily say that this small h is representing c omega. Why? See, we have pi omega c y square. Here we have pi h y square. So this h must be clearly equal to c into omega. And this h has a unit of Newton per meter. You find out how. Okay. This I leave to you to deduct why the unit or the dimension of h will be Newton per meter. Now we introduce a new parameter beta here. Okay. What you want to do is you want to introduce a new parameter. But why? You already have some constant h here. But what I'm guessing here is people wanted to find a constant parameter for hysteretic damping, which could be totally declared as a property of the material, because the hysteretic damping is arising due to the material properties. भाई एक मटेरियल के एटम्स कैसे अरेंज्ड है, उनके बीच में इंटरएटॉमिक फोर्सेस कितनी स्ट्रांग है, कितनी वीक है, ये सारी प्रॉपर्टीज तो मटेरियल की प्रॉपर्टीज होगी ना. So the purpose of the engineers or scientists when they were developing this expression was to find a parameter which could capture all the properties which were resulting in the resistance of damping in hysteresis. तो आप यहां देख रहे हो स्मॉल h तो आपका विस्कस डैम्पिंग कोएफिशिएंट को तो कंसिडर कर ही रहा है, फ्रीक्वेंसी को कंसिडर कर रहा है, लेकिन मटेरियल की इलास्टिसिटी के को नहीं कंसिडर कर रहा. भाई मटेरियल की इलास्टिसिटी कांस्टेंट जो है, कितना फोर्स चाहिए आपको उसको आगे पीछे घुमाने में, ये तो डायरेक्ट इंडिकेटर है कि आपकी इंटर एटॉमिक फोर्सेस कितनी स्ट्रांग है, राइट. तो इस के एक्सप्रेशन को भी ये इसमें ऐड करके या फिर इसमें शामिल करके एक ऐसा नया कांस्टेंट बनाना चाहते थे जो कि मटेरियल की सारी कहानी को कवर कर ले, और ये कहें कि बीटा जो कांस्टेंट है ये उस मटेरियल की इलास्टिसिटी, उस मटेरियल की विस्कस रेजिस्टेंस, उस मटेरियल की फ्रीक्वेंसी जो उस पर लग रही है, इन सब चीजों को लेकर के एक सिंगल कांस्टेंट आ जाएगा. So they were not happy with this constant h, they wanted to introduce a new constant. So that is why they introduced beta is equal to h upon k, called as hysteretic damping constant. Now finally we have something. भाई जब आपके पास में विस्कस डैम्पिंग थी तो उसके लिए आपको एक सी वैल्यू मिलती थी एक डैम्पर की, और आप बड़े तसल्ली से क्लेम करते थे कि ये जो सी है ये मेरी विस्कस डैम्पिंग की सारी कहानी को कैप्चर कर लेगा, कि एक विस्कस डैम्पिंग में किस किस तरीके की रेजिस्टेंस आ रही है, ये सी की वैल्यू आपको बता देगी. नाउ यू वांटेड टू डू समथिंग सिमिलर फॉर हिस्टेरेटिक डैम्पिंग. तो हिस्टेरेटिक डैम्पिंग के लिए आपने अब ये कह दिया कि भाई बीटा मेरा एक ऐसा पैरामीटर है, जैसे कि सी था आपका विस्कस डैम्पिंग कोएफिशिएंट या कांस्टेंट, उसी तरीके से बीटा जो है वो आपका हिस्टेरेटिक डैम्पिंग कांस्टेंट या कोएफिशिएंट हो गया. दिस इज व्हाट यू गेट. तो आप यही चाहते थे कि जिस तरह से अपन एक मैथमेटिकल एंटिटी सी लेके आए थे विस्कस डैम्पिंग के लिए, वैसी ही एक मैथमेटिकल एंटिटी हिस्टेरेटिकल डैम्पिंग के लिए भी अपन ला पाते. So this was the aim. So basically now you have this expression by not using h as a parameter because it was lacking k. You introduced k and you created a new parameter beta. And now if you see, beta is a dimensionless parameter. Once again, I leave this logical extrapolation to you guys. आप पता कीजिए कि अगर एनर्जी इज पाई के बीटा वाई स्क्वायर, तो आपका बीटा डायमेंशनलेस क्यों है, ठीक है। एनीवे, नाउ वी वांट टू मॉडल हिस्टेरेटिक डैम्पिंग। अभी आपके पास में क्या आया है, एक बीटा का वैल्यू आ गया है, और अभी आप एक डैम्पर से रिप्लेस करना चाहते हैं इसको। नाउ यू वांट टू पुट अ डैम्पर इन प्लेस। डैम्पर को रखने का मतलब क्या है, आप ये कहते थे कि कहीं पे फ्लूइड है और दो सरफेसेस के बीच में विस्कस डैम्पिंग हो रही है, सो यू सेड नो प्रॉब्लम, वी कन्वर्ट इट इनटू एन इक्विवेलेंट डैशपॉट डैम्पर। ये जो सिंबल बनाते हैं, दिस इज द सिंबल ऑफ अ डैशपॉट डैम्पर, a dashpot damper of viscosity C और the coefficient C। तो अब आप ऐसा ही कुछ करना चाहते हैं कि अगर किसी जगह पे किसी मटेरियल को बेंड और अनबेंड किया जा रहा है, और किसी मटेरियल को ट्विस्ट और अनट्विस्ट किया जा रहा है, तो इसके कारण जो डैम्पिंग होगी, यू वांट टू वंस अगेन से कि ओके, ये जो पूरी कहानी है इसको भी मैं एक विस्कस डैम्पिंग में कन्वर्ट कर रहा हूं। नाउ सी द स्टोरी इज अ लिटिल डिफरेंट। हिस्टेरेटिक डैम्पिंग विस्कस डैम्पिंग नहीं है, लेकिन हिस्टेरेटिक डैम्पिंग की जो रेजिस्टिंग वैल्यू है, जो कोएफिशिएंट है, उसको आप एक सी इक्विवेलेंट में कन्वर्ट करना चाहते हैं। तो इसका पर्पस क्या है कि अगर किसी सिस्टम में विस्कस डैम्पिंग हो रही होगी, तो उसका मैथमेटिकल मॉडल ऐसा बनेगा। अब आपके अगर किसी सिस्टम में हिस्टेरेटिक डैम्पिंग हो रही होगी, तो अब उसका मॉडल फिर से ऐसा ही बनेगा। एंड इन दिस केस यू विल से कि भाई जहां विस्कस डैम्पिंग हो रही थी वहां तो एक्चुअल सी बैठा था, और जहां पे हिस्टेरेसिस डैम्पिंग हो रही है वहां पर अब मैं एक सी इक्विवेलेंट बैठा दूंगा। नाउ दिस इज द पर्पस। आपने एक बीटा करके एक हिस्टेरेटिकल डैम्पिंग कांस्टेंट तो पता कर ही लिया है, बट नाउ यू वांट टू फाइंड वेदर यू कैन क्रिएट एन इक्विवेलेंट विस्कस डैम्पर। एक डैशपॉट डैम्पर ऐसा बना सकते हैं क्या, जिसका की कोएफिशिएंट सी इक्विवेलेंट एग्जैक्टली उतना ही रेजिस्टेंस दे जितना कि एक हिस्टेरेसिस डैम्पिंग के केस में मटेरियल अंदर से पैदा करता है। दिस इज द पर्पस। सो फॉर दैट ऑल दैट यू हैव टू डू इज, अब आपने एनर्जी ऑफ हिस्टेरेसिस कैप्चर कर लिया है, एनर्जी ऑफ विस्कस डैम्पिंग कैप्चर कर लिया है। तो अब आप क्या करना चाहते हो, इस एनर्जी ऑफ हिस्टेरेसिस को एक ऐसा डैशपॉट डैम्पर बना करके क्रिएट करना चाहते हो कि भाई अगर मैं इस डैशपॉट डैम्पर को एक साइकिल के लिए चलाऊं, तो विस्कस डैम्पिंग के कारण ये जितनी एनर्जी प्रोड्यूस करेगा या जितनी एनर्जी लूज करेगा, वो एनर्जी मैथमेटिकली या मैग्नीट्यूड वाइज एग्जैक्टली उतनी ही होगी जितना एक्चुअल मटेरियल के हिस्टेरेसिस से प्रोड्यूस हो रही है। So you are basically trying to create a viscous damper which is equivalent to the loss creation due to the material। तो material resistance के कारण जो लॉस है, उस लॉस को एक विस्कस डैम्पर के लॉस में कन्वर्ट करना चाहते हो, ठीक है। सो फॉर दैट ऑल यू हैव टू डू इज पुट दीज टू एक्सप्रेशंस इक्वल टू ईच अदर। तो अपन ने क्या किया, अब यहां पर अपन विस्कस डैम्पर का जो एनर्जी लॉस है उसको अपन अभी तक कैसा लिखते आए थे, पाई ओमेगा सी वाई स्क्वायर लिखते थे, ठीक है, पाई ओमेगा सी वाई स्क्वायर। अब अपन एक्चुअल एक्सप्रेशन लेके आएंगे कि भाई अगर मेरे पास एक सचमुच में एक टेम्पर बनाना है जिसका कि सी सी इक्विवेलेंट होगा, तो सबसे पहले तो मैं यहाँ पे सी इक्विवेलेंट लिख देता हूँ। दूसरा, जब डैम्पर आ जाता है, तो डैम्पर की जो फ्रीक्वेंसी है, जिस फ्रीक्वेंसी से आप इसको अप डाउन ऑसिलेट कर रहे हो इस पिस्टन को, वो ओमेगा ना हो करके उसकी अगर आप नेचुरल वाइब्रेशंस लें, तो नेचुरल वाइब्रेशंस में ओमेगा डी जो होता है वो ओमेगा एन अंडर रूट वन माइनस जीटा स्क्वायर होता है, ठीक है। तो अब आप यहाँ पर ओमेगा डी लिख दो। ओमेगा डी लिखने का मतलब है, अगर फोर्स्ड वाइब्रेशन होती तो ओमेगा लिखते, लेकिन यहाँ पर आप वाइब्रेट करा करके छोड़ रहे हो, तो अपनी नेचुरल फ्रीक्वेंसी से वाइब्रेट करेगा, तो उसकी जो फ्रीक्वेंसी बनेगी वो ये बनेगी। तो इसलिए अपन यहाँ पे ओमेगा डी लग देते हैं, ठीक है। एंड दिस is being equated with pi k beta y square, the actual energy loss of hysteretic damping, pi k beta y square. Y square will cancelled out, pi and pi will get cancelled out, और इवेंचुअली आप इसमें क्या निकालना चाहते हैं, यू वांट टू फाइंड आउट द सी इक्विवेलेंट, कि भाई एक ऐसा डैम्पर का सी इक्विवेलेंट कैसा बनेगा। ठीक है, तो सी इक्विवेलेंट को अकेले पकड़ लो, यहाँ पे ओमेगा डी को राइट हैंड साइड पे नीचे डिनोमिनेटर में ले चलते हैं, दिस इज के बीटा अपॉन ओमेगा डी। नाउ वी रिप्लेस ओमेगा डी विद दिस एक्सप्रेशन। ठीक है, so instead of omega d I am going to write omega n under root of 1 minus zeta square. Now see, what is this zeta in this expression? This is equal to c upon cc, लेकिन hysteretic damping में c तो होती नहीं है, so basically what you are talking about here is this c equivalent, ये जो c यहाँ पे zeta के expression में आती है, ये भी c equivalent है, और ये c जो है this is also, इसमें equivalent लिखने की जरूरत ही नहीं है, क्योंकि c जो है this is already given by 2 root km, तो इसका एक्चुअली डैम्पिंग से कोई लेना देना है ही नहीं, तो इसको cc रहने दो। तो कुल मिला के मैं ये कह सकता हूं कि दिस जीटा इज बेसिकली जीटा इक्विवेलेंट। ठीक है, तो यहां पर भी एक इक्विवेलेंट लिख दो, बट इवेंचुअली व्हाट मैटर्स इज that the value of hysteretic damping is so much negligible compared to viscous and frictional damping। बाकी जो टाइप ऑफ डैम्पिंग कौन से हैं हिस्टेरेटिक डैम्पिंग के अलावा जो अपन पढ़ रहे हैं, विस्कस डैम्पिंग है और कूलम डैम्पिंग है, लेकिन इन दोनों टाइप ऑफ डैम्पिंग के कंपैरिजन में हिस्टेरेटिक डैम्पिंग से जो लॉस होता है एनर्जी का, दैट इज रियली नेग्लिजिबल। ठीक है, लेकिन आप अभी ये क्वेश्चन नहीं पूछ सकते कि अगर इतना नेग्लिजिबल है तो इसके पीछे इतनी गणित क्यों बनाई जा रही है, बिकॉज ओवर अ लॉन्ग पीरियड ऑफ टाइम व्हेन हिस्टेरेसिस डैम्पिंग occurs, तो उसका टोटल एनर्जी अमाउंट्स टू अ सिग्निफिकेंट वैल्यू। तो इसकी स्टडी तो करनी पड़ेगी कि भाई आप इसको 1 मिनट 2 मिनट के लिए सिस्टम चलाओगे तो आप हिस्टेरेटिक डैम्पिंग को इग्नोर कर दो, यू कैन इग्नोर इट, बट इफ यू रन द सिस्टम फॉर लेट अस से 1 ईयर 10 ईयर्स, आपके एक्चुअल मैकेनिज्म्स में जो वाइब्रेशंस होती हैं, तो इसका एनर्जी लॉस सिग्निफिकेंट हो जाता है। So in that case, we need a mathematical model in place. That is why we are studying it. So anyway, the concept is that this zeta equivalent is very near to zero. Why? क्योंकि आपका बहुत minute energy loss है, and in that case, this expression would be approximately equal to omega n, क्योंकि जब zeta equivalent का स्क्वायर जीरो के करीब आ जाएगा, so 1 minus 0 is 1, under root of 1 is 1, so this becomes approximately equal to omega n. So your equivalent damping constant can be approximately treated as k into beta upon omega n. And what is omega n for any system? Damping उसमें किसी भी तरह की हो, उससे अपना कोई मतलब नहीं है। Omega n for an elastic vibration is always under root k by m। ठीक है, तो अब अपन ये जो चीज है ये इसमें डाल देते हैं। So your C equivalent would be equal to k beta upon under root of k by n. So under root of k will get cancelled out and you will get under root of k here. So eventually what you are going to get is the C equivalent. This under root of m will climb up at the numerator. This is equal to beta root k. This is what we wanted to do. So whenever you see a case of hysteretic damping, then you can say कि hysteretic damping को तो भूल जाओ, जितनी hysteretic damping हो रही है उसका एक equivalent viscous damper बनाओ और आप अपने सिस्टम में लगा दो। अब hysteretic damping को आपने बेसिकली viscous damping में कन्वर्ट कर लिया, तो आपकी गणित आसान हो गई। अब ठीक है। फिर आपसे अगला सवाल इमीडिएटली ये पूछेगा कि अच्छा, तो अब इस जो आपने कहा कि हिस्टेरेटिक डैम्पिंग को विस्कस डैम्पिंग में कन्वर्ट कर लो और विस्कस डैम्पर लगा दो, तो अब इसके आगे की गणित तो हमें आती है, इसका डिफरेंशियल इक्वेशन बनाना आता है। नाउ वी कैन मूव फॉरवर्ड फ्रॉम दिस पॉइंट ऑनवर्ड्स। लेकिन ये तो बताओ कि इस डैम्पर का सी कितना होगा। तो आपने कहा कि हाँ, इस कन्वर्जन के लिए, यानी कि हिस्टेरेटिक डैम्पिंग को विस्कस डैम्पिंग में कन्वर्ट करने के लिए हमने एक सी इक्विवेलेंट बनाया था, एंड दिस हैज एन एक्सप्रेशन इक्वल टू दिस। तो यानी आपके सिस्टम का मास कितना है, इतना किलो है। आपके सिस्टम में इलास्टिक कंपोनेंट्स का स्टिफनेस कितना है, इतना है साहब, न्यूटन पर मीटर में। और हिस्टेरेटिक डैम्पिंग जहां हो रही है उसका बीटा कोएफिशिएंट, जो कि मैंने कहा था कि टोटली नाउ अ प्रॉपर्टी ऑफ द मटेरियल। सो बेसिकली यू हैव सम स्टैंडर्ड डेटा सेट जनरेटेड बाय एक्सपेरिमेंटिंग साइंटिस्ट्स कि भाई अलग अलग मटेरियल्स का ये बीटा वैल्यू कितना होता है, और ये एक टोटली डायमेंशनलेस क्वांटिटी है। तो स्टील के लिए बीटा अलग होगा, कॉपर के लिए बीटा अलग होगा, एल्यूमिनियम के लिए अलग होगा। सो फॉर डिफरेंट मटेरियल्स यू हैव अ डेटाबेस ऑफ बीटा वैल्यूज। तो आप, हो सकता है वो किसी टेबुलर फॉर्मेट में दे रखी हो, तो वो टेबुलर फॉर्मेट से आप बीटा की वैल्यू लेके आए, सिस्टम का के रखें, सिस्टम का एम रखें, और ये जो प्रोडक्ट होगा ये डायरेक्टली आपको बता देगा कि हिस्टेरेटिक डैम्पिंग के इक्विवेलेंट विस्कस डैम्पिंग करने वाला डैशपॉट डैम्पर का सी वैल्यू कितना है। दिस इज द टोटल gist of the matter. So this was a lot of mathematical treatment. अब मैं आपको काम की बात ये बताता हूं कि आरटीयू के अंदर जनरली इतना ज्यादा मैथमेटिकल ट्रीटमेंट अभी तक हालांकि हिस्टेरेटिक डैम्पिंग के अंदर से पूछा नहीं गया है, कभी बेटा का जिक्र नहीं आया है। बट यू कैनॉट से कि आपके टाइम में ये क्वेश्चन नहीं आएगा। इट कुड वेरी इजीली क्रॉप एट योर टाइम। So you have to be prepared with this whole mathematical analysis. But generally the question that comes in RTO is describe salient features of hysteretic damping. Compare hysteretic damping and Coulomb damping. Compare Coulomb damping and viscous damping. इस तरह के क्वेश्चन जनरली आते हैं hysteretic damping से। ठीक है, राइट शॉर्ट नोट्स ऑन hysteresis damping और structural damping, इस तरह के क्वेश्चन। तो उसमें आपको लिखने के लिए क्या क्या चीजें हैं? दिस, first of all, you discuss about the hysteresis loop. You say that energy per unit volume per cycle is given by the area of the hysteresis loop. And then without the mathematical analysis in that case, you speak about the constant beta. आप यहाँ आ जाओ और इतना सा पार्ट लिखो कि equivalently if we treat the energy lost in hysteresis damping to that of विस्कस डैम्पिंग, तो ये एक्सप्रेशन याद रखो विस्कस डैम्पिंग का, ये एक्सप्रेशन याद रखो हिस्टेरेटिकल डैम्पिंग का। फिर H इज इक्वल टू सी ओमेगा आया था, बट यू वांटेड टू इंट्रोड्यूस K, so you introduced a new constant beta, and this is what you call it as hysteritic damping constant. And then you construct this equation और ये बताओ कि ये हमारा एनर्जी H है। एंड देन सिंपली, अब यहाँ पर ज्यादा गणित तो है नहीं, इन दोनों को इक्वेट करो एंड यू सिंपली write this and say that this is the equivalent viscous damping, and this is how engineers and scientists actually treat hysteresis damping in real world problems. वो उसको एक equivalent Coulomb damper में कन्वर्ट, सॉरी equivalent viscous damper में कन्वर्ट करते हैं और उसके बाद उसकी मैथमेटिकल ट्रीटमेंट करते हैं। Another very important salient point for hysteretic damping is कि हिस्टेरेटिक डैम्पिंग का जो एनर्जी लॉस है वो कूलम्ब डैम्पिंग और विस्कस डैम्पिंग के कंपैरिजन में बहुत ही कम है, बहुत ही इनसिग्निफिकेंट है। ठीक है, तो ये सारी बातें आप शॉर्ट नोट्स के तौर पे कह सकते हैं। देयर इज अ लॉट ऑफ मटेरियल नाउ फॉर यू टू राइट योर शॉर्ट नोट्स, एंड आई विल शेयर विथ यू अनदर sheet, additional sheet, which will conclusively give you a little information on the comparison between Coulomb damping, viscous damping and hysteresis damping. तो उस एक शीट से भी आपको थोड़ी सी एग्जाम प्रिपरेशन में मदद मिलेगी। So with this we will stop the topic, and I hope that you have understood at least some of it. Okay.